Hi everyone, I'm Perry and welcome back to Math Together Canada. We're excited to have a special guest joining us today, a good friend of MTC, Andi Guo. Andi has recorded 3 videos solving the 2024 AMC 8 questions 1 to 20 for all of you. In this first video, he'll be working through questions 1 to 10, and in the next 2, he'll cover 11 to 20. We really appreciate Andi's help in sharing his passion for math with our community. If you're a math enthusiast and would like to contribute by recording your own problem-solving videos, we'd love to hear from you. Feel free to reach out to us at contact@mathtogether.ca or simply leave us a message in the comments. Let's keep spreading the love of math and learning together. Now let's dive into the solutions.
Hello everyone, we will be taking up AMC 8 2024 today, and just starting off with problem 1. So what's the unit digit of this, or the sum over here? So in the street, the unit digit that we got from here is 2. We're subtracting 2, 1, 2, 3, 4, 5 times. So minus 2 times 5 equals to -8. And what this means is that we're just going back 8 steps from 10. So 10, 9, 8, 7, 6, 5, 4, 3, 2. You get the right answer. For problem 2, let me clear this. What is the value of this set expression? So immediately we can just single this out. That's just equals to 4. 44 divided by 11 equals 4. And then plus 110 divided by 44, which basically just simplifies to 2 and 22 over 44 plus 44 over 1100, but we want decimal form, so this gives us the intuition to remove a factor of 11 from both numerator and denominator, so we got 4 over 100. Well, this simplifies to just 6.54. Since this, we can just take out 22 from top and bottom and got 1 over 2, which equals to 0.5. And this whole thing over here just equals to 0.04. And we get C. Problem 3. So we have 4 squares of side length 4, 7, 9, and 10. And they're changed in increasing order. And we just want the area of the great visible region. And we can just find that and just subtract the smaller squares that take up additional space. Well, it'll make more sense when I get into it, but the largest square over here. Oh, oops, sorry. The largest white square we have here is 9 by 9, and this thing is not contributing to our space, and it takes away from this 10 by 10 square over here. So we'll just do 10 times 10 minus 9 by 9 equals to 100 minus 81 equals to 19. So that's the area of this outer ratio. Now we check this one. We'll do something similar. The gray part is just side length 7, whole area is 7 by 7, but this white square here takes away an area of 4 by 4, which equals to 49 minus 16, which equals to 33. And then we just add these two digits up. We'll just get 52 as our answer. E. Sorry. Problem 4. When Yunji added all numbers from 1 to 9, she mistakenly left out a number, so her sum turned out to be a square number. What did you leave out? So first we can just find the sum of the numbers from 1 to 9, which by the formula is just 10 times 9 divided by 2, which equals to 45. Now the nearest perfect square to this is going to be 36, which equals to 6 times 6. The only digit big enough to be able to get 36 from 45 will just be equal to 9. And this gives us E. Gives C. Right. Problem 5. Alright, Alia rolls 2 standard society dice. She knows that the product of the number rolled is a multiple of 6, which of the following integers cannot be the sum of the two numbers. So consider which ones can make up multiples of 6. 6 can go into 2 times 3, can go into 1 times 6, or like anything times 6. So 6 times anything else will just be a multiple of 6, with 2 times 3 being an exception. So we immediately go to that 7, 8, 9 can both be represented as 6 times 1, 2, or 3, and 5 is just represented as 2 times 3, which leaves 6 as the only other option that we don't have. So the answer to this problem is just going to be 6. Yep. Problem 6 now. Sergey skating around an ice rink, flying along different paths. Three lines in the field show four paths labeled PQRS. What is the sorted order of the four passes from longest to shortest? Well, so over here we can just rearrange like the path over here as path S as hypotenuse in a triangle. In the right triangle actually, path Q as just a chord and like the circumference, and path P is just even more hypotenuses, I guess. Well, basically what this gives us is like a sort of intuition that path R, because like these straight chord lines are going to be shorter than the arc that it covers, right? It's going to be shorter than the length of path P. So we already have R is less than P. We also notice that both paths S and Q are going to be longer than path P because of these hypotenuse triangles. Well, just in the right triangle, right? Side C is equal to A squared plus B squared, and this square root of A squared plus B squared, sorry. And it's always going to be more than A and B by the trivial inequality, since A squared has to be greater than or equal to 0. And in the case of a non-degenerate triangle, or a triangle that does not form a straight line, A squared has to be greater than 0. So that explains why P is going to be less than both S and Q. And we just have to find the relative lengths of S and Q, right? So when comparing these two, notice that like these parts are the same. So now we just have to find which of these zigzag paths are going to be longer. And we have this side length here as like constant between the two. So we just have and we can just call the side length C. This part equals to S squared plus C squared square rooted. And we have two of them, so 2 times that. But over here we have, and this is like half of it, right? So this is going to be C over 2. We have 2 times S squared plus C over 2 squared. Oh, that's a little bit messy. C over 2 squared. Just here, and then 2 above, so we'll just change it to 4 times that. And then we'll compare those two. We just get 2 times S squared plus C over 2 squared, or just C over 4, C squared over 4, and then versus square root of S squared plus C squared. And then when we just unbox the square roots of each, right? When we square both sides, we'll get 4 times S squared plus C over 2 squared, versus the other one, which is just going to be 4, and then times, well, not 4, just S squared plus C squared. We'll just get that this one's bigger, because 4S squared vs S squared, 2C squared, well, C squared vs C squared. And so that just gives us T is going to be longer than path S. You could just eyeball this as well and see that's pretty obvious. So we have shortest longest, R is going to be the shortest, and followed by P, followed by S, and followed by Q. It's also like the only option that gives that, so it's pretty fast to observe if you don't want to prove it. Um, Problem 7. A 3 by 7 rectangle is covered without overlap by 3 sheets of tiles. What's the minimum number of 1 by 1 tiles used? So, this one just finds like a construction, right? This one's what, 7 here and then 3 here. And then we have 2 here, 2, 4, 1. So what we can do just off a glance, right? Um, we can just see that we can cover a lot of the bottoms by this huge portion over here by these 2 by 2 shapes. And then we can fill out a bunch more by these 4 by 1 tiles. But this leaves us with like 5 open spaces, and that's clearly the worst option that we can find. So let's just like quickly see if we can do a little bit better than that. So we can just try arranging them staggered now. So maybe we can try this with this, this, with this. But that's still good, that's 5. So now we're just thinking maybe this is the best that we can do. And we can try to say, okay, maybe is there a way to make 4? So if there was a way to make 4, then oh, oops, we would have to be able to leave out either like 4 individual squares somewhere, a corner of 4, or just 2 shaped out like that, right? So now that's just extremely hard to do because that means that we will have to cover a 5 by 2 space over here, which is just impossible. And like the space over here, also impossible. We would have to leave a 1 by 1 gap, which could not be possible. If we leave 2 by 2 gaps, that's also not very possible. And the same logic we can just apply to like 3, 2, 1, but we can't really find any better 1 by 1 shape. And furthermore, this equals to 3 times 7, which equals to 21. These are 4 each, which means that we can either have 5 or 1 missing, right? And we clearly cannot have 1 missing. It just does not make sense to have just 1 square that's out because it's just not possible. But let's just use our answer as 5. So these were problem 7. Problem 8. On Monday, he has $2. Every day he gains $3 or doubles the amount of money he has on the previous day. How many different dollar amounts would he have on Thursday, 3 days later? So literally he has $2. I'll just like write that. I don't think the dollar sign is necessary. So he either pays $3 or doubles the money he has in the previous day. So when we move to day 2, he could either have $5 or $4. When we double the money he has on the previous year or adds 3. So the tricky case is what happens if doubling the amount of money equals like times 2 of x, or like some like value b times 2 equals to 3 plus 3, right? Well, or if they manage to overlap like within 1 day. But we can quickly see that that just won't really be possible because we have 5 and 4, which expands out to 10, 8. But then we can have these ones accumulate into them. So actually just might be easy to brute force this problem. So 10, 8, since the maximum amount is just 7 as well. 10, 8, and then we have 8, 7. We remove the 8 because that's just a duplicate. And then that's Tuesday, Wednesday, and then we're working on Thursday, so 20, 13, 16, 11, 14, and so 1, 2, 3, 4, 5, 6. And we get D as our answer. Alright, problem 9. All the marbles in Maria's collection are red, green, or blue. Maria has half as many red marbles as green marbles and twice as many blue marbles as green marbles. Which of the following could be the total number of marbles in Maria's collection? So G or equals to 2 times R because half as many red marbles as green marbles, twice as many blue marbles as green marbles. So G 2G equals to B. So then we can just get 4R equals to B just really quickly. So now we can just write everything in terms of R, right? So 2R, which originally equals to G, plus R, which is just originally equal to R, plus 4R, which is just the initial amount for B, gives us 7R. So we know that it has to be a multiple of 7, and the only multiple of 7 belongs here is just answer E, which is 28, and that's problem 9. Problem 10. In January 1980, the Mauna Loa observation recorded carbon dioxide or CO2 levels of 338 parts per million. Over the years, the average CO2 reading has increased to about 1.515 ppm per year. What is the expected CO2 level in ppm in January of 2030? Now your answer to the nearest integer. So we have 338 ppm plus, okay, well, let's just consider they're asking for the ppm in 1981, right? And that will just be equal to 1981 minus 1980, because those are how many years have elapsed, times 1.515 ppm is on average each year. So we can just see that we can extend this formula to January 2030. So 2030 minus 1980 times 1.515 just equals to 50 times 1.515. And then we can just do a quick approximation. So this one will just give us an additional plus 50. This part will give us an additional plus 25. This part will give us an additional plus 0.5. And this part will give us just enough to push it above 0.5. So just some small number to push it above 0.5. So if we just label this as plus 76. And then we have our current is 338. 338 plus 76 just equals to 4. Let me not make a calculation error here. 1, 4, and we get B as our answer.
That wraps up the first part of our 2024 AMCA solutions for questions 1 to 10. A huge thanks to Andy for sharing his time and helping us bring these solutions to the community. If you're passionate about math and would like to contribute a problem-solving video, we'd love to hear from you. Reach out at contact@mathtogether.ca. Don't forget to like, subscribe, and stay tuned. The second part, questions 11 to 15, is coming up next.